Hello everyone, I'm Yaoqi. Today I'm glad to present our work, Robust Peer-to-Peer Primitives using SGX Enclaves. This is a joint work together with Shruti, Tariq, Deli, Perdik, and Zhenkai. As we know, these days peer-to-peer systems are quite popular. And when we download files, we may use BitTorrent, a peer-to-peer file sharing system. And when we make payment, we may use Bitcoin, a peer-to-peer cryptocurrency payment system, which came out over a decade ago. And these peer-to-peer systems, they are allowing different nodes to join the system freely. That's why a lot of malicious or Byzantine nodes, they can easily join the system to drop, delay, deny, and forge messages to disrupt the execution of the protocol. Since most of the protocols were designed a long time ago, and the designer may not consider the security primitives against these Byzantine nodes. And that's why there are a lot of attacks on these peer-to-peer systems these days. In Bitcoin or some cryptocurrency peer-to-peer networks, the malicious nodes actually can perform eclipse attacks to eclipse the honest nodes from the network and then further perform double spend attack or the other attacks to result in financial losses for these users. Meanwhile, in some peer-to-peer privacy protocols like Tor, these Byzantine nodes actually can weaken the privacy guarantees of these protocols. For the past research, we've seen a lot of solutions for these P2P primitives. For example, reliable broadcast, random number generation. And these solutions actually can be applied for extensive applications like voting schemes, shared key generation, and cryptocurrency protocols. However, these protocols are sort of have some limitations based on their high performance overhead, and they may also limit the number of Byzantine nodes in sort of to some extent. Then in this work, we want to figure out whether we can further achieve better resilience and performance. In our approach, we want to leverage the recent trusted hardware called Intel SGX to sort of reduce the Byzantine nodes into general omission nodes. Meanwhile, beyond that, we also want to achieve better synchronous peer-to-peer protocols for reliable broadcast and also random number generation. There are well-known definitions for reliable broadcast and also random number generator. For people who are not familiar with reliable broadcast, it's quite similar to Byzantine general problem, which is quite classic. In this example, as you can see, right, we have a lot of armies with generals, and they want to conquer a city of enemies. And since we have different divisions, we want to reach the agreement that all the divisions should attack this city at the same time or should retreat at the same time. Thus, the different generals in different divisions, they need to communicate with each other and further achieve the consensus. If the initiator generals and the attack to the other generals, assume all of them are loyal, and it's relatively easy for them to reach the agreement. In this case, it's attack, basically all they decide to attack. However, if there's a traitor, then it becomes a little bit complex as different generals may receive different messages, and some generals may become confused, and at the end, the L1 general doesn't know whether to attack or retreat. As you can see, right, to solve this problem, and we propose a Strawman protocol for the reliable broadcast. We have different nodes or users, and there's an initiator. The initiator sends a message to different nodes as init. And then when the nodes receive the message, they will just send the echo message to acknowledge that I've received the message. So please, please proceed with the current message. And after 2 rounds, basically all the nodes or users, they have received the acknowledgement from the other nodes, and basically they know that the other nodes or the other users also receive the same message, and so they can reach the agreement that we can accept message M. However, this is in the optimistic scenario, and all the nodes and all the users just behave honestly, and they can agree on the same message M easily. In not that kind of optimistic scenario, basically the adversary can perform different attacks. For example, the adversary can perform execution deviation. She is assumed to send the echo message in second round. However, she send the echo message in the first round, which can confuse the other honest nodes, and the other honest nodes may reach the agreement on a wrong message. And the adversary can also perform message forgery. Basically, she can send the correct message to some honest nodes and send the wrong message to the other honest nodes. At the end, the different honest nodes may have different view on the message, and they may just have some divergence on their views, and then reach different sort of acceptance of the message. And the adversary can also selectively omit some of the messages. For example, she dropped a message to some only nodes, and these only nodes couldn't receive the sufficient number of messages. So these nodes couldn't accept the message in the end. And meanwhile, the adversary can also delay the message. For example, these messages should be sent in round 1, round 2, but she delayed the message and sent the message in the later round. Since the protocol may accept the message at the end, so the adversary can actually achieve some advantage over the other nodes, especially in the random number generation protocol. This adversary actually can look at the message from the other nodes to know that whether the generated or pre-generated message with her own message, whether it's beneficial for her or not. If it's not like a good sort of generation number to her, and then she may just drop the message or change to another random number and send it in the later round. So basically make sure that the generated random number is under her control. Of course, in a restricted model, she may not that easily to delay the message because it's in different rounds, right? And then she can just replay the message from the previous execution of the protocol. Since the message is verified and valid, and then the other nodes may accept the message, but this message can cause the final generated random number to be biased. To address these problems, existing protocols or solutions can have the way to solve these problems. However, the communication overhead is a little bit high. For example, in this solution, right? In the proper way that all the generals can just talk to each other and send a message to each other, make sure that everyone receives the message from the others. And at the same time, everyone also receive the acknowledgement of the other messages from different nodes. And then every general can calculate the majority of the messages and decide whether it's to attack or retreat. The only drawback is that the communication overhead is a little bit high. That's why, can we have another way to solve the same problem with lower communication overhead? Our solution here is hardware, like sort of the trusted hardware. If we look at the hardware, right, this is Intel SGX, which was proposed by Intel. And like several years ago, Intel started to produce a lot of chips empowered by SGX, which allow which allows user-level code to allocate private regions of memory called enclaves. And users can execute data and logic inside enclaves, which is protected from the processes running at higher privilege levels. We summarize some of the SGX features we may use, and that is enclave execution. Basically, all the data and logic are protected against the malicious operating system or the host. And inside the enclave, we can also have the unbiased randomness. Meanwhile, for different enclaves, they can use remote attestation to attest each other's logic and set up the secure channel to make sure that data can be protected via the communication across different enclaves. And at the end, we also have the trusted elapsed time, make sure that each enclave can execute the protocol in different rounds, and make sure that the data can't be like sort of delayed, or message can be delayed across different rounds. Based on these SGX features, we derive 6 properties. And next, I will just briefly explain the 6 properties. And with these 6 properties, actually, we can further reduce the Byzantine model into general omission model. The first 2 are execution and message integrity. As I just mentioned, right, the enclave actually protect the logic and also the data from the malicious operating system. And the remote attestation actually can verify the correctness of the running program. That means the enclave will just run the logic of the particular protocol we assign to the enclave instead of some random programs assigned by the operating system. And thus, the operating system couldn't like sort of change or alter the logic or the data inside the enclave. Meanwhile, we may have different enclaves talk to each other since it's in a peer-to-peer protocol. And then we use this enclave execution and further use remote attestation and all these properties to set up the secure channel and to enforce the black box computation. That means all the data, especially the intermediate states, are protected against the malicious operating system. In this way, the operating system or the host couldn't infer the information from the content. For example, if there's a random number from the enclave, the OS cannot decide whether the random number is in favor for the host or not. And then the host couldn't decide to drop which random number or data selectively. And then we also have this halt-on divergence. Since the enclaves, since the host can drop the messages, the enclave can have some ways to protect the enclave itself. For example, the enclave can detect how many messages the enclave sent out and how many messages the enclave received. Since the host may drop the messages from some honest nodes and may just like omit to receive some of the messages from these honest nodes, then once the enclave detects this omission, the enclave can just terminate or eliminate the node from the peer-to-peer network. To prevent the replay attack and also the delay attack, we have this lockstep execution and the message friendlies. With the trusted elapsed time, so basically we can make sure that the enclave is executing the logic on a particular round. If the data or message from a different round, like right now we are in round I, but the message is from round J, then the enclave will just drop the message or won't send the message out. Since we also have the unbiased randomness, so basically we can enforce for every run of the protocol or every execution of the protocol having a unique randomness. So that means in a different execution of the protocol, basically the enclave have a unique nonce for it. If we are in the execution M, but we receive the message from execution A, N, then the enclave will just drop the message to prevent the replay attacks. Thus, as you can see, right, in summary, basically we use the execution integrity to prevent the execution deviation attack. And we can use message integrity to prevent the message forgery. Further, we have the black box computation and hot-on divergence, which can help us to prevent the selective omission attacks. And meanwhile, we use lockstep execution and message freshness to prevent message delay and message replay attacks. With all the properties, actually, we can further formulate to reduce the Byzantine model into this rod model, replay, omission, and delay model. And we can also use the round number to prevent delay attacks, a sequence number to replay attacks. And for the detailed theoretical analysis, you can check the, the materials and details in our paper. So basically, we reduce the model into general omission model. And further, as you can see, right, with these SGX properties and inside this particular model, we can really achieve all the Byzantine protocols with the better performance and better resilience against the Byzantine nodes. Further, as you can see, right, when we back to this reliable broadcast protocol with all the features and properties, we can just ask all the nodes to send the messages, like the initiator send the message, the other nodes just follow the protocol, and at the end, with the black box computation and some other properties, we can further reduce the communication overhead. Meanwhile, since we have the hot-on divergence, these property can help us to actively detect the malicious hosts and eliminate the malicious nodes from the network. Further, for the random number generator protocol, since we have the reliable broadcast protocol, as I just mentioned, for the detail, you can check the paper. And then we can ask all the nodes or all the users actually to directly send the random numbers to each other. And once they received, once they reach the consensus of the protocol, and they will just make sure that they also receive the random numbers from the other honest nodes, and further, they can do the hash function of all the random numbers and generate a unified and unbiased random number. And since we enforce this trusted elapsed time to bound the time for each round, basically the malicious node cannot infer the other node's messages ahead and then produce a particular random number to bias the other random numbers. In this case, we basically prevent the adversary from looking ahead and compute the final result before the last round. And we can really achieve an unbiased random number in this protocol. Further, we can also use some tricks derived from the security properties to further reduce the communication overhead for the random number generation protocol. As you can see, right, we can just ask different nodes to generate the random number, and once the random number is below a threshold or just equal to a threshold like 0, then we can form a small group or small cluster of representatives of the large peer-to-peer network. And then we can perform the reliable broadcast protocols within this small cluster. Then this cluster can reach the agreement representing the entire network and distribute the messages to the entire network. Okay, if you look at the whole picture, the entire process is like this. So first, we asked all the nodes to basically generate random number. If the random number is below a threshold, then they are the chosen ones to form the small cluster. And then within the small cluster, they perform the reliable broadcast, and they also like generate the unbiased random number. At the end of the protocol, all the nodes will just sort of broadcast their generated random number to the others in the network. So in this way, we can really achieve a very good communication overhead and round complexity for the random number generator protocol. For the evaluation, we basically set up our experiments on DeterLab and to sort of run like 1,000 nodes on this test bed. And meanwhile, we also we also simulate the Byzantine nodes and also their Byzantine behaviors to make sure that our protocol can really work in the Byzantine model or in the Byzantine system. And then, as you can see, right, for different reliable for different protocols like reliable broadcast protocol or the random number generation protocols, the termination time are actually just like sort of sort of have the good relationship with one round termination. That means the protocols actually can terminate within a linear round. For example, in the optimal case, they can just terminate in 2 rounds. So as you can see, right, the termination time is quite constant. Meanwhile, in the Byzantine cases, when we launch different Byzantine nodes perform maliciously, as you can see, right, the time increased, but actually they still match our theoretical expectations. So basically, the protocol can really work in the real world scenarios. And with all the security properties and also the protocols for reliable broadcast and the random number generation, these protocols can be applied to different applications in the current system. For example, they can generate random beacons for voting scheme. They can also help to like enhance the random loading balancing system. So the takeaway for this work is that, as you can see, right, we can use the security properties derived from the SGX to reduce the Byzantine model into general omission model. Beyond that, we also propose some new and better performance synchronous reliable broadcast and random number generation protocols. At the end, we also have some security and theoretical analysis and the evaluation for the protocol. And that's all my presentation. Thanks for your attention. If you have any questions, just feel free to let me know. Thanks.